Good morning, everyone. Hello. I'm going to quickly rearrange. Hi. Hi. Good morning, everyone. Hi, Daniela, Saja, Sanjita. Good morning, Bradley. Hi, Isla. Good morning to you all. Hi, Gary and Owen. Good morning, Robin and Nathan. Good morning. Good morning. Yes. um, well, welcome back. We've made it to our version of Friday. Good morning, Andrea. Um, yeah, so you know we see it, today's our day to finish up chapter 5 and just do a whole bunch of problems and see, hopefully we get comfortable with everything. um, as always, you'll see on the exam resource page later today, the problems that you've seen throughout the last few days. You'll see all of those posted, and then on Friday, you'll also see all the solutions posted, all in one place. That's really what it's for, so that it's all in one place and you're able to just, quickly find what you need to study. And then, of course, Monday is a holiday. So do not plan to come to class on Monday. I won't be here. I
Are
think
we able to like extend all of our things one day since we're having everything, since we're having the holiday?
No, I don't think it's necessary. You should, yeah, everything should still be due Friday. If anything, we'll extend things perhaps next week when we are on a shorter week,
Okay.
because the day that we lose is really next week, not this week. Um, yeah, so definitely take the day off, guys, or take half a
I
day
can't.
off at the very least. Huh?
Can't. I'm already like I'm two labs behind and a homework assignment, a chapter to read. No way. No way the
So
day's off.
you can take the time off. You just have to choose to and make a plan to. So I hope at some point you find a point where all of you guys can relax and take a moment away from physics and then come back to it and continue down your list. But having that list is so helpful. So definitely, name it, write it down, check something off every few hours. You'll be all right. um, oh, that's something to bring up. Hi, good morning, Befar. We see you in the chat. Yeah, this class, it's on an accelerated schedule, right? So, um, and this is the second week, and it's the week that we got into some real physics stuff. So, if you're feeling, challenged by it, yeah, it's expected,
Overwhelmed.
because overwhelmed, yeah, it's expected because we're on an accelerated schedule. It's a 5 unit class. Good morning. um, so it's expected, and what you want to do is figure out how to deal with it, because the physics isn't going to change. Going to school to get a degree
Right.
isn't going to change. What changes is the way that you react to it. I promise you that little by little, it will get better. I know it doesn't seem that way, but it will. um, yeah, it will, guys. Take a, yeah, it will. um, Actually, what happens is that you get better, right? You get better at dealing with these things, because yeah, I'll say, oh, and then Daniela has a really good point in the chat. Planning to do a 10-minute yoga later. Yes, I'm big on meditation to deal with all the stress and anxiety, and I, like many of you, probably have like major sleeping issues, so that's what helps me too.
Absolutely.
Yeah, yeah, and exercising every day. That's what got me through my PhD. The last 2 years was exercising every single day, and it really helped get me in that mindset that I could handle anything that came my way, because I wasn't going to allow myself to fail. That's really what it comes down to. That you choose how to react. That's the one thing you can control. And when it feels overwhelming, yeah, that's okay to feel overwhelming, but it you'll get through it. So yoga, um, talking with friends, playing the guitar, anything. Yes, that was Keon in Engineering 101. Yeah, anything that works for you. Okay, so I'd like to start with our last section of chapter 5. I think we can cover it in maybe a half hour or so, and then we'll have practice problems the rest of the class, and then when I'm done with the practice problems, we'll end lecture there, and then I'll stay on and help anyone. I see a good hand clapping. Yeah, and then we'll stay on, and I can talk with anyone and help in any individual situation you might have. Um, okay. So again, all we're doing today is adding one new force from chapter 5, and we've already talked a little bit about it. And I actually did do that Google search, and you guys were all right. We're all correct that the what is it, the I think was it Nathan that was asking. Uh-huh. It was it is an electromagnetic force. So yes, of the four forces, it's the one we were talking about was not strong or weak, but electromagnetic, which completely makes sense with what we were doing, and it's going to tie into today's talk too. Okay, I'm scrolling to the slide. I'm almost there. Give me a second. Okay, I'm at the slide, and I think I'm just gonna remind us a little bit of what we did before we jump into this force. Just give you a quick 2 slide summary of everything we've done. Um, okay, and I'm about to share my screen. It's funny that you guys are planning your 10-minute yoga, because nowadays, instead of being able to go do like a 1 hour 2 hour workout like at the gym, it's all about getting little 20 minutes in wherever you can. Even when we take the break, I should tell you guys the one thing I do. Okay, the left. When we take our 10-minute break, I do 26 squats. I don't know why 26, but that's what I do just to keep my energy up and keep my head right. 26 squats during every break that we take. It doesn't take very long, and you get some squats in. um, yeah, so do something, do something. Okay, I've arranged my screens. It might be Jose for every tab that's open. Although I think I have 30 something tabs open. It counts it. Um, I really don't remember why I chose 26. Oh, I know why. I'll tell y'all later. Another story for another time. Okay, so let us just remind ourselves everything we've done in chapter 5 so far. So, chapter 5 is really looking at forces and now establishing what is the cause of motion versus chapter 4 and 2, which helped us describe motion. So, now that we understand that forces are what cause motion, we can describe that motion, the force, using Newton's laws of motion, the first law, the second law, and the third law. And the one that we will be using often is the second law of motion. The sum of the forces equals ma. And so the situations we're now looking at are situations where a particle is in equilibrium, meaning it is static, it is not moving, but we know that there are forces acting on it. And so here, when we write Newton's second law, right, we start with Newton's second law always. We would say the sum of the forces equals ma, and equal ma goes here. And I like to write this gap just so I remind myself that I actually have to add up all of the forces. I don't like this red. Okay, so when an object though is in equilibrium, then we know it's static and the sum of the forces are equal to 0. And so what you're looking at is 0 acceleration for this mass, and so the sum of all the forces is equal to 0. Some examples, right? We have a chandelier that's hanging over a table, something that's moving at a terminal speed. A terminal speed is usually the max speed that something can reach. That's what that means. Um, yeah, terminal, like almost like final, things like that. A steel beam in the frame of a building. All of the buildings we see everywhere, they all have a foundation of some sort. They have a structure, a frame that is in place, right? So all of the forces are summing up to 0 there. or a boat that's just floating on a body of water. No forces are acting on it. And so that's for a particle in equilibrium. And so we see the same for something that now is moving. A
So
particle. Uh-huh.
what I see in front of me, like, oh no, back or forward, I mean. So like we have the sum of the forces is equal to the sum of the force. There you go. The sum of the force vector is equal to the mass times the acceleration vector.
Correct.
So like if we were trying to solve for mass, we have to make the sum of the forces and the acceleration both a scalar.
Correct.
And why is that?
Because that's a magnitude. You can't add a vector to a mass.
Oh, because the mass is also just a scalar.
Yes.
Okay, I see what you're
That's,
saying.
that's why it's italicized. So, um, yeah, and that's just like like arithmetic rules of vectors. Vectors add to vectors, but vectors don't add to scalars.
I understand. Thank you.
Uh-huh. Um, so we have that the second situation that comes with Newton's second law when a particle is now acting under some net force, meaning that there is actually a number. All of the forces add up to some a summary, a net of some sort, a total force of some sort. And so then we have the sum of the forces equals ma, and this brings up a good point that here the way you analyze the situation is one of two ways. You either first look at, looking at the forces, or you can add up all the motion that you see, either in the x or the y. Once And you'll know based on the problem. For example, the first problem we saw with the hockey puck, it gave us many forces and we could add the vector components of the forces. But then when we were looking at the tension, we didn't have those values exactly. So we had to go into Newton's second law, use it, and solve for different components like mass or gravity. Um, and so then here, once it comes to time to solve, you will want to resolve this into its components and solve in terms of x and y components. And so then you'll think of the motion just in that direction, x or y. Okay, and some examples then of a particle under a net force is if a crate is being pushed across. The word pushed is the force. The word across tells us that a position is changing, which means a motion is happening. A falling object that's acted on by a gravitational force, right? That acceleration due to gravity. Or a piston in an automobile engine that's pushed by hot gases, right? The gases are contracting and expanding and moving the pistons around. We'll see that in Physics 102 a lot. And yeah, we'll focus on the gas motion there. And then a charged particle in an electric field, like putting an electron in an electric field, it's going to move a certain way. Or if you put a positively charged particle in an electric field, just because of the charges there, it's going to also move a certain way. And so now we have all of our forces that we've talked about. So the first one that we talked about was applied force. And then we talked about gravitational force. I think next came the normal force, right? And you could write that any way you'd like. And then we talked about tension. Are those it? 1, 2, 3, 4. I think.
Friction.
Oh, and today, perfect transition. Thanks, Kian. And so these are the four forces we've talked about, all our vectors, of course. And today we're going to add one more force on, and it'll be friction. And friction exists whenever there is something in contact with another object. And this might remind you of the same definition of normal force. Yeah, we're going to end up bringing in that normal force in when we talk about friction, but you'll see why it acts a little differently. Yeah.
What's that T? What's the T one?
Tension.
Total. Tension? Oh, tension.
Yeah, that's right. Tension.
Tension, applied, gravitational, normal, and frictional.
That's right. And so friction, we're going to find out you could have a static friction or a kinetic friction. So you might see S, static friction, or let's be very clear here.
So is static friction like something, a car parked on concrete, and then the other one is like where the car's driving on concrete?
Yeah, and the thing you would want to analyze there is the tire that's sitting on the ground. That's where the friction is. So yeah, that's a really good example.
But I
Is
guess there's is like the car rolling, isn't that like rolling friction or something?
if I don't know, I haven't heard the word rolling friction, but it might be used in a dynamics class. But here I know kinetic friction is the one that implies motion.
Oh, okay.
So let us formally define these, and here we go. Okay, so the forces of friction. So imagine you have some trash can here that's just standing on the ground. It's on the ground. We could very easily say, for sure, we know that gravitational force is acting on the trash can, and that's here. And because there is contact with the floor, we know that there's a normal force that's acting on it too, a normal force acting perpendicularly upward. Now imagine you have this trash can and you just want to nudge it to the side a little bit. As you start applying a force to it, the trash can still doesn't move. Why doesn't it move yet? What do we need to do?
Overcome the static friction.
Yeah, that's a really good formal definition. Yeah, we need to overcome something that's holding the trash can in place. We need to push it just a little bit harder. So, as we apply a force, and you could just call this an applied force, so that we could hopefully accelerate the trash can to the right, and I hope that's the right side. Yeah. If we want to try to accelerate this to the right, something is holding us back until we overcome whatever force is gripping the trash can to the ground. And what is holding us back is the static friction. So, this static friction will formally be defined as a force that is opposing the intended motion of an object. So, here, this force will counteract the applied force and will keep us from moving the trash can to the direction that we want. They put to the left, but I was moving to the right. So this static friction, sometimes you'll see it as that the cursive type F. Um, this static friction here will always be opposing the intended motion of this object. So if we intend to push it to the right, even though it's not actually moving to the right yet, the frictional force will be acting to the left, opposing it, right? Um, and so we can see kind of what we can, yeah, oh, here it is. Okay. So our goal then is to eventually overcome that static friction. Now, when we do overcome it, when we do overcome it, there is still contact there with that ground, and so friction will still exist. But until we overcome it, as we start to increase that applied force of pushing the trash can, we're also going to increase the static friction that's holding the trash can in place. If you were to stop pushing the trash can or push it with less force, your static friction will also decrease. So in this case, until the trash can starts moving, the applied force will usually be of the same magnitude of the frictional static force. But this is not the definition. This just tells us these are equal and opposite. But this is not how we define static friction. I'll give you that on the next slide in a second. Okay, oh, I see a question. Mehmet says, shouldn't it be f of s equals negative f because they are opposite in direction? That's a really good point, Mehmet. And if we were writing them in vector notation, then yes, they would be negative. But this is the magnitude. Notice that they're, yes, yeah, it's a completely notation. This is a magnitude. But are they opposite in direction? Absolutely. Absolutely. So here,
So
uh-huh.
so when you say like the force increases, the friction, the static friction increases. So does that
Yes.
mean like if a trash can is sitting on the sidewalk and you're not pushing it, the static friction is at a certain thing, but then as soon as you push it, but it doesn't move yet, its force increases because the static friction increased?
Yes, because the force that you applied on it increases. Yes. Um, and so one thing that might help us understand this just a little bit more is really looking at what's happening right here, right? What is it that's happening here? So if we were to just,
Oh.
take a magnified look here, you would see the bottom of the trash can, right? That's our trash can. And then you would see the floor, a nice, floor. And if we took a microscopic look, it still kind of looks the same. What if we go even deeper now and we take like a real magnified look? Well, our trash can that we see here is really made up of many, many atoms, right? So if we were to take a zoomed in microscopic look, you would see a row of atoms in some order of some sort, and then you would see the ground. The ground would not be perfectly smooth, but in fact, what you would see is like ridges, right? Tough ridges are little peaks here, and every one of these peaks has atoms all that make up the peak, right? So when we see these frictional forces, what's actually happening here is, for example, at that very position I just drew, here, this peak is actually hitting and touching the atom at the very surface level of that trash can. So they're stopping each other, which is why it's opposing, right? Um, and we have to overcome and break that bond of the atoms at that very temporary moment. We have to overcome that bond that the atoms are creating, and it is a chemical bond. um, it is a chemical bond, so it does depend. These atoms here very much depends on what material are we using, right? Yes, Daniela brings it up. She asks, so each material has its own frictional force capability. Yes. And it's really good that you guys identified that. When I say the word atom, an atom is very specific to a material. And so, yeah, although this frictional force here will move with the same magnitude as the force, there's going to be a factor there, some constant of some sort that will tell us about what material is being used. For example, you see more friction in rougher materials, and you see less friction in materials that are slippery, like ice, right, or water or oil. And so, yeah, it will depend on that. Okay,
So
let's see what.
like
Uh-huh.
so that frictional force behaves similar to the normal force. Like when you add a force to it downward, the gravitational, or when you add more downward, it increases the normal.
Yes, and I'm really glad you said that because that is the formal definition of the frictional force. And we'll see that on this, oh, we'll see it on the next slide. But you make a very good point. If we're looking at the contact, then yes, we are looking at how much normal force is acting on the object to create that contact and to bond those two atoms. So the frictional force will be dependent on two things. It will depend on the normal force, and it will depend on what material we're using. Yeah, absolutely. Okay, so we have an idea of static friction. Now let's say we push hard enough. Notice that our force vector is now much larger. Now let's say we push the force larger to the right, and now we're able to move the trash can. So now there's actual motion. This doesn't mean that contact has gone away, right? Contact is still there, and so friction is still there. But now it is called kinetic friction because the object is in motion and contact still exists. Notice that this kinetic friction here will keep this a smaller length, which is a smaller value, while the force is much higher. So we can plot where that region starts of motion. So here you can see on this graph, us applying the force is here. We start to apply some force and we still can't move the trash can. As we apply force to try to move the trash can, we're still in some static friction, right? Our static friction increases as we apply a force, and at some point, we've reached a maximum where we are now going to overcome the force of friction, static friction, and push and move the trash can. So we increase our force where we're now in a kinetic region. Now our force is enough to move the trash can, and we've overcome the hump we needed to break that bond, and now we stabilize and we have an exact value of the kinetic friction. And so what you will see is that this kinetic friction here will be due to this normal force and this coefficient of friction, which is specific to the materials. So I'll show you that in just a second. Um, okay, so we have then the friction force for an object in motion. Friction force for an object in motion is F sub K. And we can now see what all these values are in the formal definition. So here is a table of coefficient of frictions that you will often use. Let me first say that the coefficient of friction is a ratio. It's a constant. Because it's a ratio, you're not going to see a unit behind it. And it is a ratio, so it'll usually be a number from 0 to 1 because we're comparing two materials and how they act together. So this coefficient of friction table will always show you two materials, rubber on concrete, steel on steel, aluminum on steel, and then you'll see that coefficient of friction listed right next to it. And notice again, it is unitless, so it is just a number, a coefficient, a ratio that tells us about how the materials act together. Um, Oh, okay. I see Daniela has a question. Does that peak have a name where we transition from static to kinetic? I don't know if it actually has a specific name. I'm sure it does. I always, and in my materials classes, we always just talk about the region. Um, there are names for these peaks though, like a triple point, but
So
I haven't heard one for this.
so like right there, that's where your interlock brakes keep you.
Yeah, that's a very good application. Yeah. This is where like your brakes would stop you and then motion happens. No more braking.
I have a
Yeah.
question. It means the amount of the force when it's stopped and we don't push it, and until we push it to move it, it's not going to be the same amount, right? It still is.
That's right. Yeah. I think you said that you have to push it and that amount is
When the trash can is standing and no force on that, the amount of the force, the total force going to be zero, but still there is some force. And when we're pushing before it start to moving, the amount of the force going to be more than the time we don't pushing.
that's correct.
It still is standing, no moving, but it's different force, huh?
Yes, that's correct.
Oh,
Yes, that's correct. So what he's saying is that this static region force and kinetic region force are different. And yes, to cause that motion, it's true. And so here's our table of the coefficient of frictions. And so here are now your actual formal definitions of static friction and kinetic friction. So for static friction will be less than or equal to the coefficient of static friction times the magnitude of the normal force. Normally, again, this is less than or equal to, which is formally correct. But in our class, we're almost always going to look at this number here, which is just the point before it starts moving, or what is the highest point before, yeah, same thing, highest point before you cause motion. The last point where it's still static. So the frictional force, static frictional force will be the coefficient of static friction, which you see here, right? It's these values here, times the normal force. It'll always be very obvious in the problem which coefficient of friction to use. If not, it'll be given to you. It'll say, this is the coefficient of friction for this problem. So this table is something that you need to have. I will put it probably in the equation sheet. I will. But these values are given to you. You do not need to memorize this. So then we have the same definition now for the kinetic friction, and that kinetic friction will be equal to that coefficient of kinetic friction times the magnitude of the normal force. And here you would use any one of these values. And again, it'll be obvious in the problem which one of these to use and what number to use. It's kind of nice. Okay, so let's try a problem where we are going to flip around our direction. Let's see if we can, let me set a timer here so that we could stay on track. Okay, let's try this problem. You press your favorite textbook, physics textbook, flat against a vertical wall with your hand. What is the direction of the friction force exerted by the wall on the book? Okay, I see one answer from
Upward.
Henry. Okay, I hear another answer too. I see two. And this is good. Let me tell you guys, I think
And downward.
okay. We have some motion, frictional force. Okay, I have lots of B's and I hear one downward of the motion of the book, I think. So let
Every direction.
me, or like the fly goes out in every direction. Yeah. um, First, I always suggest to draw this out, right? So you have a wall and then you have, I don't know, your favorite book here, physics, of course, something like that. I don't know. This isn't a good drawing, but
Kind of looks like a praying mantis.
oh yeah, it does. um, Let me change it to green. I'll change it to pink. Okay. Um, Owen is asking, is the frictional force the same as the normal force? It's not exactly the same, but it uses the same magnitude. There's a derivation in the book to prove that to you guys. Um, if you'd like to go into it mathematically to see it, but just know that they're both forces are due to contact. So because we've established the normal force as contact, we can pull that definition in. So this is our physics book, right? Okay, and so what is the intended motion of this book if you're, what is it?
Down.
Yeah, the intended motion, this is my four-fingered hand holding it.
Oh wow.
A little buff, maybe? I don't know. This
Kind of
is
looks like a crab claw.
Yeah. And so the intended motion of this book, if we were to let it go, would be downwards, right? Downwards here. So the frictional force that's holding this up, in addition to the applied force that we are applying here, is actually upward. The frictional force here is upward. And you can imagine when the book starts sliding, um, you might even like hear that noise, right? There's contact there. And the thing that's stopping it from completely free falling is that it is still in contact with that wall. So it's gonna fall. It's still gonna fall due to gravity, but that wall is gonna have an effect on how it falls. And so, uh-huh.
So are you able to increase the friction by increasing your pressure on the book?
Yes, that's absolutely correct. Yes.
So in
That
so like, does that increase the coefficient of friction or no? The coefficient of friction remains the same. Oh, that's that constant upward, like ramp.
yes,
You
yes.
pushing and pushing and pushing. Okay.
Yes. Okay. So the answer is upward, and so you want to my definition of frictional force, the direction is opposite of the intended motion. I don't know if I've actually seen that written somewhere, but that's the one that really makes it connect for past classes. Opposite of the intended motion. And I have to include the word intended, or else we all flip out. Okay, so Randy
For
brought up
which force is that?
the frictional force, the direction, opposite of the intended motion. That's my CLE definition. It helps me keep track of it. Opposite of intended motion.
The static frictional force or the just
For both.
static, right? Oh,
Both.
for both. Okay.
Yeah. And then it'll be, oh, I guess the word intended doesn't belong when you're using kinetic. But yeah, when the actual thing is moving, then it's opposite of the motion. But when it's static, it's opposite of the intended motion. I think that's why we put the word there, intended, because actually, I think it was the last Physics 101 winter class that was arguing, but the book's not moving. It's like, well, it's intended motion. Okay, and so this is good. Yes, the answer is upward. And then Randy brought up the word ramp. So let's try ramp and let's see now the definition or what we would see in an image when something does have friction. So there's a lot going on in this problem. So we're gonna stay here for a minute. The following is a simple method of measuring coefficients of friction. Suppose a block is placed on a rough surface, inclined relative to the horizontal as shown in the figure. The incline angle is increased until the block starts to move. show that you can obtain the coefficient of static friction by measuring that critical angle at which this slipping just occurs. So we're labeling that maximum value of the static friction at the angle, the critical angle, but that's just our own label. So let's look at the image. First, you see that there's a curvy surface here. This is your clue that it's friction. There is friction. That's what you will see on any picture that is cueing you that there's friction. Then you see a block that's sliding down here. Now, we can look at all of the forces that are acting on it, and you want to create your origin of where you're going to place everything. Typically, we say X and Y. You will find in some of these problems that it is to your benefit to flip the axis, and sometimes you want to flip the axis in the motion, so that one of the axes is parallel to the motion. So our intended motion is to go to accelerate the block eventually this way to the diagonal, right? What is that? The southeast, right? Southeast or so. So we are going to flip our axis this way to the X axis pointed down that way and the Y pointed down this way. When we do this, our vector and our free body diagram will nicely align on this axis. Did we know that beforehand? No, we just chose it to be parallel to one direction of motion so that it hopefully matches. Now we can look at this block and draw our free body diagram. We know that gravity will always act on this object, and gravity is always pointed down, center seeking. It'll always be pointed down no matter which way the object is oriented. So notice this is just straight down, F sub G. Our normal force is always exists when there's contact, and the normal force is perpendicularly away from that contact point of the two surfaces. So you can draw your perpendicular indicator there and draw in your normal force. Right away, we see that the normal force lands on our y-axis. So that's going to be really nice. We don't have to break that down. Now, our intended motion here is going to be on the x-axis here. And so a frictional force exists that is keeping the block from moving, and it's a static friction, and it is opposite of the direction of intended motion. Opposite of the direction of intended motion also happens to lie on the negative x. So this tilting of the axis really helps us out. And again, you are the chooser of the origin. You can make the reference frame anywhere you'd like, as long as it works for you and it's consistent. Okay, so looking at this, of course, the force of gravity is going to have to be resolved into its components. And this is a special case, but a very exact case. Now, if I break down this component here, which is typically what I would see as my y component, the angle theta here, this is my y component, the angle theta here is what? Opposite or adjacent to this side here?
Opposite?
Yeah, I hear lots of people say opposite. I see Bradley in the chat too. It's opposite. So even though this component, which is typically what I would visualize as a y component, it's now lying on the x-axis, and it is still the opposite side. So this is still going to be the magnitude of the hypotenuse, which is mg, times that component, that opposite component, which is sine theta. And then if we look at our angle again, and now we look at what we would typically see as like the x, it's now actually lying on the y-axis. And theta here, this is going to be its adjacent side. And because it's adjacent, even though it's on this y-axis, we are going to use cosine theta. So the magnitude of the hypotenuse, times cosine theta will give us the adjacent side. You want to be very clear with that, and this picture very nicely tells you that this angle theta is the same as this angle theta. So now that we've split this up and broken it up into its components, we can start doing a little bit of physics with our equations. We've already done some, but yeah. How do we feel about this diagram and the way it's angled and getting the sine theta on the x. We okay with that? Okay, I see some thumbs up. So we'll do another example, another similar example where we flip the origin again like that. Okay. All right. Yeah, we'll see another example like that in the future. Okay, so what is it that they asked us in this problem to solve for? Oh, okay, mu sub s. So where do we find mu sub s? We find this in our definition of static friction here, right? Mu sub s equals n. So let's look at our free body diagram and start adding up all of the forces. We always start with Newton's second law. If you don't know where to start with Newton's second law and break down everything in terms of its x and y components. And remembering that now this is the x direction and this is the y direction. Notice that our block is not moving. We want to get to the point where it's just at its maximum angle before it starts moving. So this is a static block. So we sum up the forces in the x direction. Only look at what's happening in the x. And here we see mg sine theta minus the magnitude of f sub s. So Mehmet, this is the negative you were talking about earlier. Now in magnitude and in component form, that negative does come out because it is opposite. And this whole thing is equal to 0. Then we sum up the forces in the y, and this is static, so it equals 0. And we look only what we see in the y for our free body diagram. And you see the magnitude of the normal force minus mg cosine theta. And this whole thing then is equal to 0. So up until this point, the physics is done. Now it's all about the math and figuring out what is our best way of solving for the coefficient of static friction. And remember that this coefficient of static friction lives within the definition of static friction here, or this variable here lives within the definition of static friction, which is here. So this static friction is right here. So the first thing I would suggest is to rewrite this, right? F of s is equal to mg sine theta. Now, can we use the second equation? This is equation 1. Can we use the second equation and somehow take something from here and plug it in there?
Can you isolate m?
mg, yeah, we can isolate mg because this mg here is the same as this mg here, right? So what will this be? N equals mg cosine theta, n over cosine theta equals mg. I think that's right. If that's wrong, someone tell me the right answer. Okay, so then we're gonna plug that in there. So let's do that now. So our first equation was the static friction is equal to mg sine theta, and we're going to plug in this mg component n cosine theta from equation 2 in there. So now we have n cosine theta times sine theta, and these two become tangent theta. So now we have the static friction is equal to n tangent theta. Okay, now we can use our definition of our static friction, which I didn't finish here, or I wrote wrong, right? We can actually use our definition here and plug that in. So our definition for static friction is the coefficient times the normal, and we bring down the rest of the equation. We are looking for that maximum angle, so we can call it the critical angle now. The n cancels out, and now you're left with this. This is your answer. And notice there are no numbers, but we were also given no numbers, right? So you should expect to have no numbers in the problem because you weren't given it. In fact, you were just asked to find what is the angle in general. I hope the math of this makes sense. The physics behind it is really interesting because look at what happens here, guys. This tells us that this static friction coefficient will depend only on this angle, and it will not depend on any forces on it. Now imagine this angle changing from a small incline to a bigger incline to a higher incline to a higher incline, and realizing that the masses do not play a role in when the block is going to slide. That is physically what this is telling us. The masses do not play a role in when when the box is going to slide. This is what Galileo? Yes, Galileo Galilei. Yes, this is what Galileo did in his house under house arrest, right? When he was trying to study free fall, his argument was that the masses. Thank you, Saja, for answering Henry's question. Yeah, when Galileo was trying to prove that he was saying in vacuum, um, any mass will fall at the same rate due to gravity. This is basically saying the mass isn't important here, that there's the same thing of gravity acting on all of them.
But if the mass of the object is bigger, won't it like have more force downward on that ramp?
Yes, and that normal force will counteract it.
And then
You're absolutely right, but the normal force will counteract it.
oh, so like pushing down on the box wouldn't help the box stay only because your hand is staying on the box. But if you just put more weight in the box, it wouldn't stop it from going down the hill.
No, it's not going to stop it. The only thing that'll stop anything from moving down in this situation is the angle theta. It's really nice to see when you can see this mathematically. Okay, I see lots of questions in the chat, so let me see. So Henry was asking, where did the n cosine theta come from? And Saja answered it, solving for the mg. I'll circle it up here. This n cosine theta came from here. And this n cosine theta came from equation 2. So it came from the sum of the forces in the y direction. Yes, like the feather and the hammer on the moon. This is absolutely right. The masses, we come to find out now, aren't actually true.
So like pushing that book up against the wall doesn't keep it there because you're putting more pressure on the book. It keeps it there because your hand is up against the book.
Yes.
Okay,
Yes.
so we didn't increase the friction by pushing it onto the wall harder.
No, because there's no motion yet. You only increase the friction when the motion is happening or when you're applying a force in that direction. The force of the hand on the book is just creating a larger force of the wall against the book, equal and opposite.
So like you increase, so like I thought you increased the friction. Oh, okay, so the coefficient of friction is not changed by the mass, but the amount of friction is.
Yes, yes,
Okay.
the amount of friction can change, yes. And then Amir says cosine theta from the line perpendicular vector of n, then saw, oh, okay, yeah. Isla, are the coefficients from that other chart on flat surfaces? You know what, I think they are, Isla. I think that's a really good point, and I think they are on flat surfaces, yeah. How would you calculate how the coefficient changes with an angle? How would you calculate so the coefficient never changes. The coefficient is atomic bonds, so literally one bond of I don't know iron, let's say iron bonding to a much smaller carbon atom. So the angles here don't matter. What's at play here are electrical forces, and electrical forces, the direction is taken radially. So the shortest distance between them. So angles won't make a difference in the coefficients here at all. Now, when you asked about flat surfaces, I think you mean compared to like this angle here, right? So friction will exist no matter where, no matter how it's angled, if there's, as long as there's contact. So the contact is only there because of the two atoms that are touching, not because they're angled at some point. Yeah, if you have another question about that, Isla, put it in the chat, let me know. We can continue with it. So to be clear, the coefficients will never change. The coefficients are relationships between two known materials, always.
But I'm sorry, Professor. Isn't so? But that mu s is the static coefficient of friction, right?
Yes.
And but then so it's saying that the degree changes the static coefficient of friction.
I see what you're saying. So the way that this works is to identify the type of material that you're looking for. Um, so this static friction will be at the maximum point that these two blocks will be allowed to stay static. If you have a different angle, you probably have two different materials that you're sliding and not the exact ones. Okay.
Makes sense. Thank you. Thank you.
Yeah, I see you nodding. So yeah. And then Isla says, is it pretty much saying that the angle is the smallest angle needed to move T? Yeah, this critical angle is going to be the angle that will be the last angle before you start causing motion. If you increase that angle anything above the critical angle, you're going to cause things to move before you're going to needed to move it. Yeah. So this angle is the maximum angle that will keep this block static. If you have a different angle and the block is moving, you're probably using two different materials, right? You'd have to find. I'll take you back here. Yeah, you'd be using two different materials if you found a different coefficient of friction for a different angle. So the one way, had we been in class, we would have done this experiment with a ramp, and you would add blocks to angle it, and you would measure the static friction for different blocks of material, for wood, for Teflon, for rubber, even for glass, and you would find different angles at which that block is going to start moving, right? A different material is going to give you a different angle. Okay. Yeah. I think, man, I really wish we had the lab. But picture that. Picture sliding something down, and depending on what material it's made out of, it's going to slide at a different angle. Yeah. Oh, you know what? Now that I have this on here, I usually do this in my materials class, but let me just take a minute to show you guys. Look at how large the values are for rubber on concrete, and think about rubber on concrete is 1. So you're taking 100% of that value of the normal force, because rubber on concrete is really rough. Now, as you go down, you start to see things like Teflon on Teflon, right? Or waxed wood. I don't know what dry snow
That's
is.
skiing.
Huh?
Skiing.
Ah,
Waxing on dry snow.
oh, okay. Thank you. That's this one, right? Skiing. That's what you guys are
White
saying.
powder is the best.
Okay. I didn't know that. So skiing is nearly frictionless, right? So you see here, there's no value. I'm not really sure what the no value is, but on wet snow, look how small that value is, which means that whatever the normal force is, let's say the normal force is 100, you're going to multiply it by 0.14. 100 times 0.14 reduces the number 100 down to 14, right? So the frictional force that's there is only a tenth of the normal force of you acting on the actual ground. So you're going to slide. You're going to slide because 10 is much smaller than 100. So notice what these numbers actually mean as they get smaller, and make that connection to the different materials. For example, right, our joints in humans, there's like liquid between our joints, right? And we don't feel any type of friction there. That's why that number is so small. So when we apply a force of some sort and we're using our joints, that frictional force 0.01 is going to reduce whatever we're feeling. So we're not going to feel it. Anything times 0.01 is going to be really small, right?
Like when we're running, so like that's kind of, does this make sense where like you get stiff when you're not moving, and it hurts, like my joints hurt when I'm stuck and I'm not moving, but
Yeah.
like when I run you feel great because
Yes. Has anyone ever had that thing called runner's
knee?
No, not runner's knee. It's a thing that you have here. You can't see me or standing, but it's like right below your stomach. And anyways, I read about it. Um, a pinch,
A
runner's
side
pinch.
A
stitch?
stitch. A stitch.
Yes, you guys got it. Runner stitch. If you ever read about this, I got it before, and it completely has to do with the lubrication that's between like your rib cage and your skin, and
Oh, I didn't know that.
yes, and the impact of the force. So when you're impacting and you're running or jogging and you're hitting a certain way that isn't appropriate, that lubrication is going to either move or somehow not be where it needs to be and cause pain because we don't
So
have
like,
that coefficient of friction there.
so like
Yes, Owen is right. Uh-huh.
when you like tense up and hold your breath, that helps that.
Yeah. Yes. So that's the way. So there's two ways to solve it. Owen is right in that you need to be very hydrated before you start running. And the way to solve runner stitch is to fix your breathing so
Yeah,
that,
like shallow breathing and stuff helps a lot.
yes, yes.
I always thought it was like a, I've said, I have a side stitch, but I always thought that it was like cramps or something. I didn't know what it was. That's so cool.
It's all physics, guys. Everything can be explained by science. And that's what physics is. Yeah, that's what you exist. I mean, that's everything can be explained by science. Everything. Anything, yeah. And Daniela, how do you account for air resistance in free fall? I'm a little perplexed by this. So I'll just quickly tell you guys since I think we have time. Yes, Owen got it. So when you're free falling, the reason we are not actually falling at 9.8, we reach a terminal velocity before we get to that acceleration. And the reason that is because we're not in vacuum. There are air molecules all around us acting on us. And literally, and not just air molecules, other things in the atmosphere too, right? And so whatever's in the atmosphere, those molecules are physically hitting you. And when it contacts you, what's the force that you feel when when anything's in contact with you? Anything in contact, it's friction, Mehmet. Yes. So that friction is causing a upward force, right? Your intended motion is down, so the friction is up. So you're never going to reach acceleration when you're free falling in air. You're going to be very, very close to it, very, very close to it, because we know friction is small, but it makes a big difference in some things. In fact, what happens, you'll learn in Physics 102, is that friction causes motion of molecules. Actually, the other way around, right? Yeah. No, friction causes these motion of molecules, and the way that this energy is dissipated is by heat, not necessarily by moving us a physical distance, but by heat. Yeah. A question from Luis. Yeah, so Owen, you're totally right there. Yes, it's not. Yes, that is the missing piece, Daniela. That's right. And then Luis, so would that compare to holding your hand out of the window of a moving car? Yeah, feeling that force, that air that you're feeling, Luis, is air hitting you, air resistance. It's kind of funny because that actually cools us down sometimes, right? But no, if it were at an incredible speed, it would be heat. It would be heat due to friction. Okay, well, I'm telling you, I can go on forever. If this stuff interests you, take the materials of engineering class. You'll have a good time. We go deep into this for every material. Okay, let's try one more friction problem, and then we'll maybe take a break and try some more problems. I should say that there's nothing new. After this point, after the friction you've just seen, we're not adding anything else. So up to this point, we're now just practicing problems. Okay, a hockey puck on a frozen pond is given an initial speed of 20 meters per second. Uh-oh. If the puck always remains on the ice and slides 115 meters before coming to rest, determine the coefficient of kinetic friction between the puck and the ice. Okay, so before we pull out information, let's look at what's happening here. You have your hockey puck and its motion is to the right. Because the hockey puck is on the ground, we know a normal force exists between the hockey puck and the ground. And because we know gravity is acting on it, the force due to gravity is pointed downwards. Now we know that there is motion here, and so we know that there is also contact, so a frictional kinetic force will exist. frictional kinetic force will exist opposite to the direction of motion. And so that's what you see here. And so this is our free body diagram. Notice that we do not care how the hockey puck started moving. Not of interest to us, not in the timeline of the story. Okay, now let's look. Now let's pull out information. Nothing has changed from chapter 4. Okay, so initial speed of 20 meters per second. We know how to write this. V initial is equal to 20 meters per second. Nothing has changed here, 20 meters per second. If I had more space, I would always take the time to write 20.0. It's only because I'm here, but you guys build those habits. If the puck always remains on the ice and slides 115 meters before coming to rest, so this means that it has changed position from final to initial, whatever final to initial is, it has moved 115 meters. And then what else do they tell us? That it's coming to rest, right? Coming to rest. So V final is equal to 0 here. Okay, and now they're asking us, what is the coefficient of kinetic friction? And we know that this is somehow embedded into the definition of frictional force here. So our clue is, let us look at Newton's second law, do the free body diagram, sum up the forces, see if we can get this force here. And, you know, there's a clue here that perhaps we might need our kinematic equations because they give us all these other values too. Okay, is that everything? Yeah, I think that's everything. Okay, let us move over to the next slide and start solving. So always start with Newton's second law after you have your free body diagram and see what information you can get there. So we sum up the forces in the x direction. The motion here means that we are accelerating. There is an acceleration here in the x direction. And so the sum of the forces in the x equals ma in the x, and the force in the x, we look here, all we see is the negative frictional force. That's it. So minus F sub k equals ma. Now we look here. What motion do we have in the y direction? Do we have any motion in the y direction? No, we do not, right? So the sum of the forces in the y will equal 0, and we look on the y-axis, n minus mg. Okay, now up until this point, again, we've stopped physics, and now we need to do some math and try to figure out where we're going to get these values from, right? Okay, so I don't know. There's plenty of places to start. You could start by subbing in the information here, and you could even make some relationship here with this n. So let us start. So here's our first one. We take the actual definition of the frictional force, and this frictional force, kinetic frictional force, is minus mu kn, right? This whole thing is equal to max. I think we got that there too. Now, if we take our second equation here and we say n is equal to mg, right? All we did was move over the mg. We could sub in this n here, and this n comes from here. So the frictional kinetic force is minus mu n, where the n becomes mg. So this was n minus mu k n, or mg, is equal to that mass times acceleration. So this is this equation, and this is this equation. And we subbed in the n from the second equation. I hope we're okay with that so far. Okay, and now...
It's just, I'm sorry, it's just I'm surprising. I didn't think that it would be like so... I don't remember doing this much substitution in Calc 1 even last semester, but there's a lot of very rigorous substitution, it seems.
And I will call it problem solving, right? It's a technique of problem solving because little by little, you need to identify what are the direct substitutions that you want to make. Are these the first, is this the only way to solve it? No. You could cycle through a million substitutions and still get the same answer, but this is the direct way. And hopefully you start to see them a little more obvious, but it won't always be the case. Yeah. Okay, so this is the equation that we're left with here, and now we can cancel out these m's, and we're left with minus mu k times g is equal to acceleration of x. I think I just realized that I never told you that this is mu. My bad. This is mu, little m. So now we're left with this acceleration, right? We're left with this acceleration and minus mu kg. So our goal was to solve for this value here. We have gravity. We want to solve for mu k. So we need to solve for now this acceleration. And let me remind you, we were given the initial velocity. We were given the change in displacement, and we were also given this final value was equal to 0, and this is equal to, I think it was 20, something like that. So you want to pull in your kinematic equations, right? And there is one, it's not the big kahuna one, but there is one that says the final velocity is equal to initial velocity something minus 2ax. So that's the equation you want to use. This is it. Oh, it's here. Yeah, vxf squared minus vxi squared times plus 2 times a times the change in displacement. And if we go through our list, you can see that we have everything that we need here, right?
The mu k n came from the fk.
Yes. This fk is equal to this.
Oh, it's there and there.
It's there and there. Yes,
Okay.
I really hate the way this was drawn out, but I can't. The whole thing is a block of equations, so I can't change it. But yeah, they wrote it twice and then put its equal thing next.
Why, Professor? I have a question about the first. It says sum of the forces in the x direction is equal to minus the force of kinetic friction up top.
Yes.
And I was wondering why it was negative. Is it just because it's pointing in the other direction,
Yeah.
into the left as opposed to the right?
That's exactly right.
Okay, that's fine.
And this will kind of help us there, right?
Right. Okay.
So remember, our overall goal is to find this acceleration. So now we can start solving for this. Before you put numbers in, of course, you could put the 0 in because the 0 is easy to handle. But before you put numbers in, do the algebra just to not confuse yourself, right? So we can put the 0 in. We have v initial 2a. This is going to be a 0 also, or you can just consider it, displacement, change of x. It's up to you how you want to write it. And so this equation will reduce down to this, or this step first, vxi squared 2a times x final, or that change in displacement. You could call it either one you want. And now we can sub in what we know. Ax here is equal to minus mu kg. So this is ax. And this is good because we don't know that acceleration, but we're trying to solve for it, right? Okay, and now we're left with this equation, and our goal, I think, originally was to solve for this guy here. We know the rest of these values, and so we can plug everything in and isolate that mu k and plug everything in. So there's mu k. We've brought it over to the other side and divided by 2gxf. And now we can plug everything in, our initial velocity, our gravity, and our final distance. And you'll see that all of the units very nicely cancel out. This squared is applied to the meter and the second. So you have meter squared second squared here. And here you have meter times meter over second squared. So this is meter squared over second squared. And so that cancels out, and we're left with a unitless coefficient of kinetic friction, 0.177. How are we doing? What can we clarify about the math here? Or take some time to follow the slide and you'll see it. It's just a matter of following the way that they're doing it. Yeah. I think it's really nice too. So where is the physics here? Let us see. Um, you know, uh, this is our physics here. Um, Identifying this is our physics here, and then the rest is all, math, substitutions galore. Yeah, one student, very, very, very good student, like one of the top ones I can remember. He, like many of you and like me, did not like the textbook problems because he's the one that said to me, they take you on it's like math acrobats. They flip you all over and they have you go searching for things that you haven't used in forever, you know. Yeah. So this is
And they
also
don't necessarily explain those either.
no, they of course they don't. They want us to like, yeah,
Like you're
yeah,
just like, what's this? Why is it here? But
yeah,
they say, oh, it is, so you know it's right, but you don't have no clue why.
yeah. And I gotta say, guys, that even when I go over these myself, I go over these problems at least 3 times to figure out, what is their order, and I have to read the book and the slide at least 3 times. I never get it the first time it's given or shown to me. I can get most of it, but to get a complete understanding where I can answer your questions, and really believe what it is that I'm telling you guys, at least 3 times of everything. Okay.
I was reading. Oh, I'm sorry. I was reading like reviews of this book or something, and I guess people do, yeah, like go through every problem in the book, like when they're taking like the going grad school for physics or something. It's
Yeah.
because they are difficult problems.
Yeah. So when you are applying to grad school, you got to take the GRE, which is the graduate record exam, similar to the SATs from high school. And you got to take a general exam for the most part. And in sciences, you got to take a subject exam. And the physics GRE is one of those exams. All of the questions are based on the first 2 years of physics, and it's these, and they ask you very supposedly very straightforward, like the ones you saw in the lab of the identifying variables. It's just a one-liner, right? This satellite is orbiting at this speed. This is the radius. What is the period? And you just gotta zoom through them, and it's at least the wording is clearer. But the problems in the book take longer. They're meant to challenge you. They're meant for you to go through a process that includes feeling challenged and overwhelmed and then coming to a goal that you've completed it. So it's all okay. Okay, so I have at least only three more problems to show you, 2 or 3 more that I'd like to show you from the last stuff, not the friction things right now, but just some problems that we didn't get to go over yesterday that I'd like to go over if you guys, if we're all up to it. Let me just see. 1, 2, 3. Yeah, it is about 3 problems. We'll see how far we can get. So do we need a break? Can we walk around, or maybe we should take a break? Okay. Yeah, let's just take a break. Let's come back at 11:15. Yes, I could use some squats too.
11:15 now.
Oh, I'm sorry. 11:30. That's what I meant. And then I'll come back to Bafar's question. Yeah, yoga time. I'm gonna go do some squats. We'll all come back 11:30.
Okay, see you then.
See you soon. Yeah. I'm back. I hope some of you are back too. We're almost there. Oh, okay, I see some thumbs up. I see some people. Excellent. um, hi everyone. Hello. And I see a question. Bafar, you want to ask a question?
Yes, my question was about the efficiency. I think the efficiency is kind of the friction, right? For
Can you
example,
speak up?
my question is about the efficiency. For
Oh,
example,
yeah.
one transformer has a like 65 or 70% of efficiency. The rest of energy is kind of friction between the atoms or molecules, right?
Yeah, so that brings us back to the question you had in the chat. His question originally was, so the efficiency in a device or electrical circuit is some kind of friction that's bringing down the efficiency. Yeah, that's correct, because there's motion of electrons there. And when they're hitting each other and colliding with each other, they're causing friction that'll build up heat and will bring down that efficiency. Also because it's causing a zigzag motion of electrons versus a straight path, right? So yeah,
Even in electromagnetic forces, still there is a friction, right?
yeah, that's true. Yeah.
Uh,
Um, okay, so let me take us back in time to a different problem, where we were going to do this problem yesterday, but this is just good practice. Oh my gosh. And let me like emphasize too to everyone that right now we're just going through problems. So yeah, if you if there's anything else you got to do, the recording is still going to be here, but we're just going through problems right now. Nothing new for lecture. Okay, let's try this problem and think of our sum of forces. This is the next problems I'm going to show you are before the friction section, so you shouldn't see anything about friction in these next problems. Okay, so here, this is called the Atwood machine, which is a lab you would have done in class too. A lot of movement. Okay, when two objects of unequal mass are hung vertically over a frictionless pulley of negligible mass, as in the figure, the arrangement is called an Atwood machine. The device is sometimes used in the laboratory to determine the value of g by measuring the acceleration of the objects. We want to instead determine the magnitude of the acceleration of the two objects and the tension in the lightweight string. I don't remember. Oh, we will calculate the tension. Yeah, so magnitude of the acceleration and the tension that's here. Okay, so the first thing is they tell us it's a frictionless pulley of negligible mass. So nothing about the pulley will matter in this problem. So let us look at what we have. First, you see two masses that are unequal, M1 and M2. We can say or deduce that mass 1 is the smaller one here because mass 1, according to this arrow, is moving upward, right? So that's the one that's going to be pulled by mass 2. And that's what this arrow tells us. This arrow is telling us the direction of motion. That's an O. The direction of motion. So this is accelerating upwards. It's accelerating upwards, and that is what we're calling positive. Now, as this mass 1 accelerates, this mass 1 will dictate how mass 2 accelerates and vice versa, right? So the acceleration that we see in mass 1 is the exact same acceleration that mass 2 is going to experience, but in an opposite direction. So when we look at these situations, we're going to split them up into two scenarios. But notice that the acceleration in situation 1 for mass 1 will be equivalent to the acceleration in mass 2. The only difference here is that we are creating our downward motion here to be positive, to kind of be in line with the one from the first situation. So just imagine that they move together, right? One moves with the other. Okay, so let us create our free body diagram for each of these and see what we come up with. So when we look at mass 1, of course, we model it as a dot, and It's mass 1. And we know that gravity has to be acting on it. And so gravity is downward. Now you think about the tension. What is the tension that the ball is experiencing? The tension is pulling the ball upwards and holding it up. If the string was not holding the ball up, the ball would fall. So even though it's moving upwards with some speed, there is still tension there between the string and the ball. And the tension will be away from the object, parallel to the rope. And so here is the tension. And notice the way we drew the arrows here. The tension is much larger than gravity because we are overcoming the acceleration due to gravity and moving upwards. So our tension is higher there. Okay, I think that one's all right. Now we come to the second one. The second one is mass 2, and we know that gravity is acting on it. So we have a downwards arrow, F sub G. We also know that the rope is attached to the mass, right? The rope is attached to the mass. And when the rope is attached to it, even though it's moving downwards, what is causing it or keeping it from free falling is the rope holding on to it. So that rope has tension being applied to the box. So if we look at this box and we think of the tension is away from the object and parallel to the rope. And so here we are for the second one then. The tension is upwards, but now our force of gravity is much larger here because we're moving downwards. So we know that the tension here will not overcome the gravity because we are moving in the direction of gravity. How are we with the free body diagrams here, especially with the tension? I want to make sure that we get the tension. Okay, I see some thumbs up. Thank you all. Okay, so now that we have our free body diagrams, we can move on. What is our usual thing, right? And I see a question from Noah, and I'm going to get right to it. Do the tensions cancel each other since they are in opposite directions? Very fun, very interestingly, no, they won't cancel each other. And notice that they are pointing in the same direction, but we have different positives. So you're right in that they're going to have different magnitudes. The direction of the magnitude is opposite. But we are going to look at these scenarios separately. So we're not going to look at them together, but you will identify that the tension that this rope is going to apply to this object is actually going to be the same magnitude of the tension applied to this one. And they are opposite in direction. They will not ultimately cancel each other out because we're going to work with them separately. So no, they don't cancel each other out. But I see why you're saying that, because the directions are opposite and the magnitudes are the same. And another question, will we have tension 1 and tension 2? No, because this rope is the rope is what's applying the tension. So the tension is the same. The tension here is equal to the tension here, just like the acceleration on M1 will be the acceleration on M2. Those are both very good questions that you guys are asking, good details to make sure we understand. So no, there's only one rope applying the tension, and the rope applies the tension the same way on both objects. Okay, so let's start with Newton's second law. And of course here, I hope you see that we do not have any motion in the x-axis. So we're only gonna sum up the forces in the y. And we'll start with object 1. So if we look at object 1, and we know that positive is upwards here, we can say T minus M1G is equal to the acceleration M1AY. So the sum of the forces equal MA. And for object 1, it's tension minus M1G is equal to MAY. Now this AY here is going to be the exact same acceleration that M2 will experience. So pretty soon we're just going to write AY equals A because it's the same. Eventually we will. Okay, so we're done with the equation of the first object. There's nothing more we can do. We can think about it, but nothing more. Now we look at the second object. Sum of the forces equal MA. The sum of the forces equal MA. And our A here is positive because we made our acceleration here downwards be positive. That was part of our initial frame that we made for the second scenario. So knowing that downwards here is positive, then M2G is positive. So the sum of the forces equals M2G minus T, because now this is in the negative. Because we made that assumption in the beginning. Now, could you solve this the other way around? Yes. Will you get the same solution? Yes. As long as you're consistent with how you add up and subtract everything according to your drawing, everything will still be equivalent. But this is the way they chose to do it. And it actually, for future engineers out there, we're drawing free body diagrams right now, but eventually you're going to also draw something called kinetic diagrams, KD, which separately show the motion. And that's this arrow here. So this arrow is the start of a kinetic diagram, because the motion will be different than the forces. But wait till you get to Dr. Navarro's class. You'll you'll see it there. Okay. So
quick question. What happens to the T, to the tension?
Like the next step?
No, I mean just I'm probably just missing some, but just you know, the M2G minus T, I just don't get where the T is going.
This T here?
Yeah.
Positive over there on the other side.
And this T here? So I think you guys are still thinking that they're going to cancel each other out. They're actually equivalent to each other, but in different directions. So let us do this. Watch what we're going to do mathematically. Because the T is the same in each one of these equations, let's make this equation set up for T. And let's say M1AY plus M1G. And let's do the same here. Let's solve for T, because you guys are correct. The tensions here are going to be equal in magnitude, but opposite in direction here. So T here is equal to, oh, this one's harder. I'm going to add the T to that side, then subtract this guy. Okay, so M2G minus M2AY. Do we agree so far?
Yeah, I'm sorry. I was just reading it wrong. I was reading the equal signs as like arrows instead. Like I thought. Okay, never mind.
Yeah, I totally get that. Yeah, these are two separate equations, and they're written the full line out. So now we have these two T's. What you want to do now, so up until this point, everyone, the physics is done. We now solve mathematically, try to solve for these, either for tensions or acceleration. Once we solve for these tensions here, you can see that we can equate the two tensions. Yeah, we can equate the two. So if we set them then equal to each other, this top T will equal this T over here. So these two values will equal each other. I'm going to have to erase it.
So the sigma of both of the forces in that direction do not equal each other?
No.
They're zero.
Huh?
They're not zero, but they equal each other?
They're not zero, and they don't fully equal each other because one is going to move. If they were equal to each other, then they would stay balanced.
So like the way it's written there, it looks like they're the same, right?
No.
Like
I see what he's saying. He's saying like, because in equation 1 we have the sum of f in the y direction and also in equation 2. So maybe you can write like the sum of f of like m1 in the y direction and the sum of f in the y direction of m2. You know what I'm saying?
Yeah.
That might help out.
That's why I wrote the 1 and the 2 here, but this is for mass 1. But I see what you guys are saying, that they look like they're equal. The sum of the force y, sum of the force y. These are two different equations for two different scenarios.
So we're setting their equals equal to each other, like the m1g negative m1g plus m2g is equal to. So isn't that essentially saying, okay, so because we manipulated it further?
Yeah. So
because they both have the same tension, so you can equal them to each other.
Yes, they have the same tension, so we're going to equate this T from equation 1 to the same tension on equation 2. And what happens is basically what Noah was saying.
Oh,
They cancel each other out. They don't cancel, they equal. They're equal. So now we're going to take these two equations, equate them to each other so the T goes away. But I
oh,
don't
so
want,
it's like a system of equations, like because you have t and t is the same for both.
yeah, so let's keep solving it. And let me finish, guys. So we equate these two equations for t, and now you're going to rearrange the variables so that the like variables are on one side and the other ones are on the other side. So for one equation, we have m1ay plus m1g, and the other one we have m2g minus m2ay. Let's move all the ay's to one side and all the g's to one side, to the other side. And so that's what you have in this equation here. After we've equated them to each other, after we made them equal, after we make them equal, we then move the gravity all to one side and the accelerations all to the other side. This part is math. You just have to subtract things around. For example, this m2ay is negative, so you're going to add it to this one, and that's where you get this equation here. And then you'll have to, then you could subtract this one over to the other side to equal m2g, to add with m2g, and that's what you see here. Yeah, so M1 and M2 are not equal. In fact, the problem tells us that M1 and M2 are unbalanced. They are not equal to each other. Okay, so now when we've combined the accelerations together, we can solve for what the problem is asking us for, and that's AY. So we can take away AY from each part of this equation, and we'll have M1 plus M2 times all of AY, and we bring that over to the other side, and here is your solved problem. You isolate AY, right? AY comes out of the equation here. So M1 plus M2 is now one product, and that's here. And then you can isolate the G, the gravity also too. And then you'll have M2 minus M1, M2 minus M1. And that's what you see here. And so we've now solved for the acceleration, which is what the problem asked us to do. The next thing that they asked us to do is to solve for the tension. So now you can plug this into your favorite tension equation. You have two options and just plug it right in. They plugged it into the first one, right? And so from here, you could see that this equation for tension came from this one. You could plug it into the second one if you wanted to also. And you plug in your acceleration equation, and this does take like 2 or 3 steps of manipulating around, but it's all algebra. You plug in this value here and distribute everything, rearrange, and you will end up with this equation here. But it'll take a moment. How are we now with this math?
I'm good with the math, but still on the first, the sum of the fy in the first equation and sum of fy in second equation, you say is not the same, right?
Correct.
But we using the part of that in the first one and the part of that one from the second one equate together. It makes kind of the confusion, you know.
So your first statement said the sum of the forces are not equal. That is correct. The second statement you said is, but then we're using one to plug into the other, and that's the confusing part. But you're not using the sum of the forces plugged into the other sum of the forces. You're isolating the tension, and the tension is equal in magnitude for each because it's coming from the same rope. So as a whole, the equation is not equal to each other. Individual components are equal to each other, and that's tension here. Yeah, so tension is the thing, and that's the trick that you're going to use in several of these problems, is finding, one equal to the other between x and y, or two y's or two x scenarios, and then plugging them in.
That very last part, the 2m2, that part right there, where did that come from?
So this is from plugging in AY. After we've solved for AY here, we isolate AY. Now we plug AY, because this is one part of the problem. It says solve for AY, so we box that. The second part says solve for tension. We take the tension equation from the first equation, and now we plug in AY there. And this is long, and you have to arrange it the way they do. You want to distribute everything out.
So wouldn't that be like G plus 2M? Like,
You have to take the time to distribute it.
okay, so this is just the final.
Yeah, there's no way that you're gonna see it. It takes me like, because I do every step out, and it takes me like a solid 4 or 5 minutes of writing it all out. You have to distribute it all out. But if you were to like leave the problem just like this, it's correct. It's absolutely correct. But they are just making it pretty for you guys. But you will have to distribute every single part out so that you could rearrange it for it to look like this. Yeah. So just take the time to distribute it and prove it to yourself. Yeah, that is nice of them, but it's also very frustrating because I've done it like 3 different ways, and the only way I was able to get it to look like the way they show it is by distributing every component out and then recombining, which is annoying. But it's pretty. So we thank them. Yeah, attitude of gratitude, always, guys. Yeah, we thank them. So this is our tension. Yay. Okay.
I forgot what the question was.
Yeah, the question was, what is the magnitude of the acceleration and the tension?
So that we have the magnitude of the tension, but not the magnitude of the magnet. What?
No, what is the magnitude of the acceleration and the tension? And so here we have both.
Oh, okay.
Yeah, here's the acceleration and here's the tension. Yeah. Okay, so let's think about this now, right? Think about what it is that we have. So you guys tell me, what if I am balancing, if I have 100 pounds and 100 pounds on each of my hands, and they're in a pulley. If I have the same mass on each side of the pulley, are they going to move?
No.
No, that is correct. What if I take 5 pounds from one side and add it to the other side so that now I have 95 on one and 105 on the other? Which one are we going to move? Yeah, we're 105 is, yes, 105 is going to move down.
Even just if you remove the 5, it'll move, right?
That's right. Even if you just remove the 5 and don't add it to the other side, but we're in a whole system where things transfer, right? We move the 5 over. So the point is that 5 pound difference and adding it to the other side that now causes a one side of 95 and one side of 105. That mass difference is what causes that motion. That little bit of difference between the two masses is what causes that change of us being able to move now. And so we can see that throughout the equation, that the only thing that causes the motion here, the acceleration, is the difference in the masses, is this value here. This is the factor that'll tell us, right? And you can think about it just as you're holding two things. By shifting one mass to the other, the difference is what causes that motion of acceleration. What if we look at a system, this system now, and m1 equals m2? We should see no acceleration, right? That's correct, but mathematically we can now prove that here. So here you would have m1 or m2, what was it? m2 minus m1, and then I think it was m1 plus m2, something like that. But if the masses are equal, we can further just call them m, and m plus m here will be 2m, but m minus m will cause our 0 here. So mathematically, we can still see that this, of course, is correct. And then what about the second scenario, guys? What if I take one mass move 99 pounds over to the other side. Now I have 1 pound versus 199. What will be the motion?
Very quick.
Very quick.
Very fast.
Yeah, it's gonna zoom, right? So what if one of the masses is much larger than the other? Let's say M1 is greater than M2, then M1 is going to fall as if M2 were not even there. Or like you guys say, very, very quick, right? Mathematically, what does that look like? If M1 is so much larger than M2, then we can disregard M2, say it's insignificant, right? This goes to 0, as close to 0 as possible. And what we're left with is something free falling in that direction. Now, M1 is the one that's greater here, right? And it's falling negative G. So let's just be clear here that M1 is the one that would be falling and in the negative direction. That's why that shows up there. Wait, is M1 the one that's falling? Yeah. 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 So mathematically, we can prove all of these things. Okay, let's try another problem. We're very good on time, so we're just practicing problems here galore. Okay, what about this one now? A car of mass M is on an icy driveway inclined at an angle theta as seen in this figure. Find the acceleration of the car assuming the driveway is frictionless. So they only want us to find the acceleration of the car here. Okay, so something else that they give us the angle theta and they give us this x-axis here. So this is, and the motion of the car is in the direction of the x-axis. So
Cosine of theta is equal to, no. Oh, I'm
hold
sorry.
on,
I thought I was
almost there. Yeah. Oh, we're almost there. So again, notice they put the acceleration of the car along the x-axis. That helps us out. So we can draw our y-axis here, and we can always start with our free body diagram. You know that the force of gravity is going to act on this straight down. And of course, this is going to have a x and y component. We know that the normal force will always be perpendicular to, so perpendicular to. And notice that this very nicely is going to be parallel to the y-axis. This one will not be. And then we also assume here, is this friction? No, frictionless, it's frictionless. So those are the only forces that we have acting on this right now. So we can solve for this. So again, we tilt our angle to be our axis to be in the direction of motion of the car. And just to remind you of that, this is parallel to the x-axis. And so we have our force of gravity pointed down, our normal force perpendicular, which is also then along the y-axis. And now we can resolve our gravity into its x and y components, right? This component here is the opposite of the angle. This is opposite. So it's going to be mg, the magnitude of the hypotenuse, times sine theta. Right? Sine is opposite over hypotenuse. And then this component here is the adjacent side of that angle. And so this will be the magnitude of the hypotenuse times cosine theta. And so now we start with Newton's second law, right? As always. So we can start in any direction that we want. Some of the forces in the x direction, then we look only along the x-axis. What is being added in the x? Only mg sine theta, and this is also the direction of motion. So the sum of forces in the x equals max, and the forces are just mg sine theta. We look along the y-axis, right? Along the y. There is no motion along the y. It says may, and this does equal 0. Convince yourself there's no direction. There's no motion along that horizontal axis. It's only along the x-axis. Yeah. So even though it says ay, this is equal to 0. Okay, so then we have the normal force minus mg cosine theta that you see here, and this whole thing is equal to 0. And so they asked us to solve, I think, for the acceleration of the car, right? So this one, you have different ways to do it, but you probably just want to use that top equation right here. Cancel out the masses, and you have ax is equal to g sine theta. And this is very similar to friction, right? The motion is due to the angle. And here we kind of see some resemblance of that. The acceleration is due to the angle here too. Okay, let's bring in some, let's make this a little bit harder, right? Okay, suppose the car is released from rest at the top of the incline, and the distance from the car's front bumper to the bottom of the incline is a distance d. How long does it take the front bumper to reach the bottom of the hill? And what is the car's speed as it arrives? So they're asking how long, t, and what is the speed as it arrives. When they're asking for speed here as it arrives, that says to me final speed. Yeah. What is that final speed? So let's see what the problem tells us that we can actually pull from, right? The car is released from rest. So this is v initial is equal to 0. At the top of the incline, and the distance from the car's front bumper to the bottom of the incline. So let's say this is the car at the top, and they're asking what is the distance from here, the front bumper, to here when it reaches that. They're giving us that distance. That value is called d. We can also call this the change in x, right? Change in position is equal to xf minus xi, but they want us to use the letter d, so we are going to use that. How long does it take? Okay, so given this information, let us try to solve for what we have here. Okay, so they are asking for the time. They're asking for time, and we have the change in displacement. We have initial velocity. They're also asking for final velocity. We'll do time first. And remember, from the first problem, we also have the acceleration. So if we have this, does a kinematic equation come to mind, anyone? Ideas? We're looking for time. We have x final, x initial, we have v initial, and we have acceleration.
Like velocity final equals velocity initial plus acceleration times time?
What is our final velocity? We don't know that yet.
I don't know.
Yeah, we don't know this one yet. Right now, we're going to solve for time. But you hold on to that one. It's our big kahuna equation. I know you're all saying it out there, whispering it to the laptop. Yeah, it's our big one, right? We know x final, we know x initial, we know v initial, we know acceleration from the first problem, and we are looking to solve for that time. And so if you put in the zeros, the easy ones right away, x final, x initial, this becomes the letter d here. V initial is 0, so this whole thing goes to 0. And so all that's left is d is equal to 1/2 axt squared. And now we can isolate and solve for the value of t. And t is equal then to the square root of 2d over a sub x. And we can now put in what is our equation for a sub x from part A, which was g sine theta. And so now we have a value of t. So now they want us to solve for the final velocity. And remember again what we were given, right? They want us to solve for final velocity, and we have initial velocity, we have the change in displacement, and we have acceleration.
So the equation that I said is this equation differentiated or integrated.
So that is the derivation of one of the equations. Can you say that again?
So this equation, the final position x, is that equation integrated. The one that I said, like the velocity final is equal to velocity initial plus acceleration times time.
So you're saying that the integral of this equation is equal to this?
No, I'm saying it's equal to the equation above. No.
The kinematic equation, right?
Yeah, yeah.
Yeah. Okay, I see what you're saying.
Because like that's where you get your t 1/2 t, because you take t plus.
Does that work? I've never
Yeah.
seen that.
Then your constant is the xi.
Yeah, I hear you. And I see that if you integrate with respect to x, right? Or dt. I don't know if that actually works, but if it does, it makes sense to me because final integral of final velocity, I think would
Because
equal.
like if you integrate, like integrating velocity gives you position. So you know that your position, your velocity final is now your position final, and your velocity initial is now your position initial.
Yeah, and I'm with you, and I see that the integral would work, but this equation comes from a definition of average acceleration, where this one tells us instantaneous. But if there probably is a scenario if everything was continuous, oh, but then there wouldn't be acceleration. I don't know. I see where you're going with this, Randy, and mathematically I could see that it could work. So I've never thought of it that way. Take the time to integrate it, like not in class, and do it out. It would be cool to see if it worked, because I see what you're saying from it. It could work. Or someone else, because that's a good way of thinking about it too. Okay, so our goal is to find this final velocity, and we're still given these here. And so we can take one of our last kinematic equations that we have, v final squared equal to v initial squared plus 2a times that change in position. We can take that kinematic equation and plug everything in here. What you'll see is that the v initial goes to 0. And when that goes to 0, you're left with v final squared is equal to 2 times a times the displacement, which is that change in x. And then we take the square root. And after we take the square root, you have the final velocity, which is what they were asking for, the final speed, right? So this comes from this kinematic equation, and we solve for final velocity. So from the free body diagram, we first got the acceleration. After that, with some more information, we can use the kinematic equations to solve for time and for the final velocity here. Yay! Okay, so that's just another example. I have one more for you guys if we're up for it. let's try it. You know, I think there's a longer lifespan in scientists and engineers because we're gonna keep practicing these math problems. So it's okay, it'll help us out. Okay, something similar to what we've seen here. A ball of mass m1 and a block of mass m2 are attached by a lightweight cord that passes over a frictionless pulley of negligible mass, as in the top figure. The block lies on a frictionless incline of angle theta. Find the magnitude of the acceleration of the two objects and the tension in the cord. Hey, didn't we just do this? We did something similar, huh? Okay. Okay, so let us kind of analyze the situation similar to Atwood's machine. We have M1 and M2. One is, they're not equal, right? So there's going to be some motion here. And we're going to say that M2 is going to be heavier, so it's going to cause motion this way downwards, this diagonal downwards acceleration. And it's going to cause M1 to accelerate upwards. So this is a clue here that you will also want to look at these situations separately. So if we look at the first one for M1, The free body diagram for M1 is here. Our axis stays the same, X and Y, and one of, our direction of motion lies along the Y axis. And so you have the force of gravity acting on the ball downwards, F sub G. And you also have tension acting away from the object and parallel to the rope. You have that force of tension also acting on ball 1. Okay, easy enough. And notice acceleration here is upwards. So this, luckily we can still keep our same positives. Now we look at block 2, and that's here. Block 2 is it's completely different free body diagram. And we're gonna angle that axis again to be along the direction of motion. So we are accelerating in this direction also, the same direction as X. Okay, so of course you're going to have a force of gravity acting down on it, and that's what we see here, force of gravity. The normal force is going to be perpendicular to that surface, so perpendicularly out, perpendicular to that surface that's there. And our tension is going to be away from the object, parallel to the rope. Away from the object, parallel to the rope. And so that's what you see here. Are we okay? Okay, thank you. And very nicely, again, we see that tension and the normal force lie on the X or Y axis. So that'll help us out because we can break down the gravity force pretty nicely. We've done this already. Okay, here's our free body diagram. We're going to take this over to the other side and start to analyze the situation. So let us look at the first one. So always start with Newton's second law here, and you see the sum of the forces along the Y, and we only add up what we see along the Y here. The sum of the forces will equal mass times acceleration, right? T minus M1G, the tension minus M1G. So that looks okay. And this is equal to the mass times the acceleration in the Y. Now, notice that they make this change to the A because the acceleration in the Y here is going to be the same acceleration that the other object experiences no matter in what direction. So we are making the change of A sub Y to equal A. You'll see where this comes in right now in the second object. Okay, so this is for object 1, and this is for object 1. Now let's look at object 2, sum of the forces in X and Y. The sum of the forces in X, and notice we're just using X prime to differentiate from X. That's it. That's what the prime is for, only reason. So we don't get confused. So now we have X prime and Y prime. So the sum of the forces in X prime are equal to MA in X prime direction because we are accelerating in that direction. AX prime. Okay, and so we look here on this axis and we have M2G sine theta minus T is equal to M2 times AX prime. Okay, we have some good resources from Nate. I'll say that in a second too. Thank you, Nate. Okay, and so AX prime is the same acceleration that is being experienced by block 1 as block 2. So we can make this jump of calling AX prime just A. And this will help us then equate the two eventually. So now we look in the Y direction, some of the forces in the Y, and we just add along the Y axis the value of N minus M2G cosine theta, and there is no motion in the Y, so this whole thing is equal to 0. So very similarly to what we did in Atwood's machine, we want to start equating things and getting rid of variables because there are several unknowns here. The question is asking us for acceleration. So let's try to solve, for acceleration and tension. Okay. So
Professor, I'm sorry. I don't get why the acceleration is the same for object 1 and object 2.
Yeah. So if
it is though?
It is because they're attached to a string. So one dictates the other, right? Do you see it here with the image? Are you laughing because you're like, oh yeah, duh.
I get it. Yeah, duh. They're attached by a string. Yes.
Yeah. Yeah. Um, okay, so let us keep going and trying to solve here. So what can we pull from equation one? We can make everything here equal to tension, right? So maybe that'll be our first move here. Yeah, it's a long week, I agree. So let's move this over to this side, right? And then we can make an equation here. I'm gonna move that one over and write the equation. Actually, I think it's just gonna pop up. So okay. So we take from equation one, we have T is equal to, we brought over this to this side and then we take out the M1. Tension is equal to M1G plus A. This comes from equation one. T is equal to M1A plus M1G. And we just took the M1 out and isolated it. So there. Okay, so what can we do with this tension now? Well, we see from our two equations in the second set that there's a T right here, right? So we can start to plug things in like we did before. So let's take equation 2, fx prime, m2g sine theta minus what was originally T. This is T. And we're going to plug in this T into equation 2. So at the very least, we've gotten rid of tension, and now we can solve for acceleration, right? Because the idea is that you know the masses and that we can calculate this angle or the angles drawn on the image for us. So let us solve for A, and we rearrange. We do a lot of rearranging here. The way that you get this is that you distribute this out. Distribute this out and then move the M1A over to this side. And when you then remove the A again, you'll see M1 plus M2 there. As long as you see that, you'll see the rest. Ah, okay, or it's easier to solve for T for both equations. Yeah, that's another way. Solve for T and equate the two. Totally easy. I like that way, but you have to eventually make that connection that you're just equating the two T's. But this is the step-by-step. Okay, so now we have our acceleration. Now that we have acceleration, we can just plug it right back into our tension equation. And you can pick, again, whichever tension equation you want to use. The one from the top is fine, right? You could plug this whole acceleration back into this equation here or this equation here. They're the same thing. And redistribute and then rearrange, and you will get this value for the tension. Yay. So this is the equation for both. The answer for acceleration.
What were we looking for anymore? I don't remember.
We're looking for acceleration and tension.
So the acceleration in the rope, or the acceleration of the object and the tension in the rope.
Yes. And that's here, right? Find the acceleration and tension. So see how it's very easy to get lost in what it is you're doing in these problems, which is why you really want to be organized in what are your given variables. Very like blatantly write it on the paper. What is it that I'm solving for? Either make a separate column or use a different color. Yeah. Mehmet says, where did the sine theta plus 1 come from? This totally comes from the addition here. I think what happened is M1 and M2 distributes out. So you actually have to do the distribution. Maybe after class I can show you, but if you plug in A into this equation here, plug in A, let's see if we can just write one step of it. It's really long. G plus this whole thing that has another G, and then close it off. So this whole thing goes into here. Yeah, so you got to take the time to do the math, and I promise you, it's nothing but algebra. It's nothing more than algebra. I think I have a picture somewhere of solving it all out. I'll look for it, for the actual thing, just so you can confirm. But it's good practice for you guys to do it too. Okay, so looking at these solutions again. You want to just look at what is it that it's telling us, right? Acceleration here, some difference in the masses, but there's a factor of that angle because M2 is inclined. And then with the tension here, because the two are attached, there's a product of the masses here also times this angle. So let's see what it means, kind of on the other side. What happens if this situation, if theta were instead 90 degrees? Let me show you. What happens if instead this theta were a full 90 degrees?
It would go faster.
It would certainly go faster because that incline wouldn't be there, but it actually acts like an Atwood machine, right? That incline goes completely away where now the pulleys are just hanging one over the other one. Yeah, the hardest part of calculus is the algebra. Man, that's so true. And the calculus is just the algebra with extra steps. Yeah, it's patterns of the algebra. So this becomes an Atwood's machine, and the easy way to do this is to solve the acceleration and put in theta equals 90 into sine theta here, right? This sine theta becomes 1, and you see the exact same equation that represented the acceleration in the Atwood machine. And so then you put in theta here too, and you put in theta here, you'll get 1 plus 1 equals 2, and 2 times this whole thing, and we get the exact same tension that was given to us in the Atwood machine. So you see that this angle here is really dictating a lot of what's happening. And that is, again, what Galileo studied. He studied small inclines because he could not, when you drop something, it's really hard to get that interval of time when you're dropping something, I don't know, unless it's like really high up. 10 seconds isn't going to show you a lot. So instead, he studied small inclines. Yeah. Oh, one more. What if M1, the small mass, is equal to 0? Then this describes a mass that's sliding down an incline, right? It's similar to the sliding car problem. So we no longer have the thing that's hanging down here. What if M1 is equal to 0? Then you have this problem here. And then you can see mathematically that will work out too. If you put in 0 into M1 for the acceleration, it'll go away completely. And this is what you're left with. And remember that this was the solution here. A is equal to sine theta g. Okay. I have wonderful news, everyone. We are done. We are done. Those were all the problems. And I usually don't get to go through all of the problems in every single class. So I'm very, very proud of us for having time to go through all of these problems that gave us extra practice, I hope. Questions, comments about this part before I stop sharing the screen?
So, if we haven't done any of these problems, like I haven't done any of them, and then, so if I have questions over, I know, not if, I will have question on probably every single one. And so how do I ask about them over because like the way these go on I feel like the way the stuff it shows on these like slides doesn't like equate to when I'm solving a problem for myself, So like, what do I do to rectify that? Because the tutoring isn't open over the weekend either.
Right.
And so like,
step 1 is always trying to reduce all the mumbo jumbo from the wording. So try to draw the image or they should give you an image sometimes. If they don't give it to you, try to draw it. Step 2, take out all the numbers and all of the clues that they give you to make your variables, right? If something is at rest, things like that. Pull that out, pull all of that out. You want to simplify before you build a bigger problem than what is really presented. Because that's part of this, is dealing with, it's gonna seem impossible to solve, but it's not, it really isn't. We just have to break it down. So draw a picture, and step 2 is list down everything you have and what are the equations that you can work with. And then really focus on what it is they're solving for, what it is you're solving for. And once you figure out what it is, okay, they want the acceleration and tension. What am I missing to get to the acceleration and tension? It won't always be obvious, but you definitely want to try to get through it. Yeah.
So not being able to solve problems is why I use Slater to like show me how, because I mean, I don't really know how to do any of this stuff, but I mean, I'll look at the equations we go over in class, and then I'll just go to Slater and I'll be like, okay, I messed up this problem, and they'll show me the exact way how to do it. So I mean, that's, you know,
Yeah, and
how I, yeah.
you put that in the chat too, so everyone just make sure you saw that. In case anyone uses, Nate put this, uses the website Slater to help them do homework problems. I found that by using the free VPN hotspot shield, you can bypass the free. Okay, that's yeah. You guys read that.
I can explain it. So when you use Slater for our book, there's a limited number of solutions that you get for free because it's like a quote unquote college textbook, which is stupid. So I found a way to cheat past it. Because it's they base your free solutions off of your IP address. So if you use that free VPN hotspot shield, you just download it, and then you know, when you use up all your free solutions, you just turn the VPN off and then you turn it on again, and your solutions are like reset, you know, so you have infinite free solutions. And yeah, so that's cool.
That's great. And I think, Keon, did you say earlier that
Yeah.
incognito?
That also works with incognito mode on Chrome, and I haven't checked with Firefox or anything.
Okay,
I'm
so
gonna try that out.
that's perfect. I love to hear all these solutions, and yes, people are saying thank you. So if the incognito doesn't work, then try the VPN to hide your IP address, right, or give you a different one. Now, let me say, guys, you put a lot of energy into figuring out how to get these solutions for free online. You can use part of that energy too, a little bit on the problems, or just keep in that very determined mode.
Yeah, I think that's where we differ because I just paid for it. I just skipped the effort and just went, okay, I'll pay for it.
I can't afford to pay for anything, so I have to, because I'm really broke, as you know.
Too, but
as a college student.
I couldn't handle the stress.
But Randy, see, that's exactly it. That you paid for it so that you would bypass the stress, but the stress then won't go away because now you have to figure out how to solve the actual problems, right? You just move it around. You move around the stress to places where you can handle. But overall, guys, you are going to feel challenged by these problems. You are going to feel stressed. You're going to feel like, where the heck do I even start? The first step is know that you can solve these problems. Start with that mindset. Start by staying in any little bit of positivity and writing down things you can. And I promise you, you will get points for writing stuff down. Just don't leave things blank. And the solutions to guide you are a really good technique to use. Also, don't get stuck in the details. I gotta say that the best discussions in this class come from physics questions, but most of the questions that are asked in this class are actually math questions and questions about, did I get this right? But the physics of it is what you really want to get. And I promise you, I'll try to match your physics understanding to your grade. But unfortunately, we have to go through this process of me showing a product for your grade, right? So keep trying. I want to see you guys get comfortable with having to go through the process of not knowing how to solve these problems. Yeah. Oh, I see just a comment really quick to me. I know this is not mechanics, but I think it's still physics. Do we learn this equation this term? It's a Schrodinger's equation. Schrodinger's equation will come in at Physics 103. It's so funny. I was just looking at this meme last night on Schrodinger's equation, and I was thinking to myself, it's so funny that this is quantum mechanics But at the heart of the math of Schrodinger's equation is just looking at how things change. But you're looking at how things change in space and in time. So you're doing partials, and second order partials. Yeah, but it is physics 103. That's correct. Yeah, it is physics 103. Okay, so it's exactly 12:30 on the dot, but don't leave just yet. I just want to see if I can make one quick announcement. Super quick. Hold on. Don't leave. Don't leave. I appreciate you guys not leaving. Don't leave. Let me just see if I can get this up really quick. Okay, your class's exam average was an 87 on exam 1, so that's really good. I actually think it's a little bit higher, just because if I toss out one of the lowest and the highest, the average will shift a little bit closer to 90. So very, very well done. I think you should be able to see the grade. If you can't see it, let me know. I think it's visible. And if you want to see my notation on your exam, you could click, I think the button is called like feedback or something. Yeah, feedback. It's on student mode, so I can't actually see it, but a student showed me once, and I think it's feedback. And then you can see I wrote up on your exam. If you emailed your exam to me, I will do those tonight. So I did not get to those, and yeah, for whatever reason, if it's not on Canvas. Yeah, that was the last thing I wanted to tell you guys. So use that motivation that you did very well on exam 1. You know, carry that over. You'll be okay, I promise. Okay, that's all I got. Lecture's over. Have a good weekend, everyone. I'm gonna stick around. Bye. I'm gonna stop
Thank
recording. Yeah, no problem.
Thank
Bye.
you, Professor. Thank you so much.
Yeah, you're welcome.
Have a good long weekend.
Yes, everyone, enjoy your Monday. Do something. Go for a walk. Bye, guys. I'm gonna stay. I'll stop recording in just a second, but I'm gonna stay. Bye, everyone. Bye, Gary, Robin, Nathan, Daniela. Have a good one. Bye, Robin, too. Oh, yeah, you said it twice.
Monday is off, but what happened the quiz?
Yeah, Monday is a holiday, so the exam will be on Tuesday morning. Monday is MLK Day. Bye, Guadalupe.
All right. Thank you.
No problem. Bye, Bafar. Thank you.
Have a good weekend.
You too.
Can I ask a question?
Yeah, of course you can ask. Nate, I'm glad you stuck around to hear that. Okay, and some example problems. Okay, great. Yeah, let's start with questions. Let me stop recording and